Um, Welcome everyone to today's webinar organized by CellPress on tackling stability challenges in silicon-perovskite tandem solar cells. This type of solar cells have made significant performance leaps in the past 5 years, surpassing power conversion efficiencies of 30% and garnering significant interest in industry as a potential photovoltaic technology for large-scale renewable energy generation. The stability of these devices, however, remains a concern and a critical issue to solve towards real-world applications. So we need to improve our understanding of the fundamental physics that governs this mechanism, as well as focus on device design and development that can address these issues. So designing new approaches to overcome these degradation processes remains really a critical endeavor for the PV community. My name is Elisa De Ranieri, and I am the editor-in-chief of Newton, which is the CellPress journal dedicated to physics. My colleague Cheryl So, on the slide here, is the mastermind behind this event. She worked together with other colleagues that I'll mention in a second to put this together. She can't be here with us, unfortunately, today, so I will be moderating the panel on her behalf. And as I was saying, she worked with some other colleagues from CellPress, namely Andrew Wadsworth from Joule, which is our energy journal, and Chuming Ma from Cell Reports Physical Science. All of these journals that I've mentioned, Newton, Joule, and Cell Reports Physical Science, as well as another journal that we publish, iScience, we're all interested in publishing content that is relevant for this webinar. So today we're really honored to have three distinguished speakers for this panel. Stefan de Wolf, who is a professor in material science and engineering, as well as the chair for material science and engineering and applied physics program at KAUST. Joy Luther, who's a senior research fellow at the National Renewable Energy Laboratory, and Anna Maria Petrozza, who's a senior researcher, principal investigator, and center coordinator at the Italian Institute of Technology. They will each give a brief introduction about themselves and their work, and following their presentations, we will proceed with a panel discussion on the latest advances of silicon-perovskite tandem solar cell technology, specifically discussing stability issues and challenges and how we can work towards developing robust solar cells based on this technology, both from the point of view of fundamental research and applied research. After this, we will open up the floor for questions from you, from all attendees. So if you have questions for the speakers at any point, you can use the Q&A box on the right of your screen, where you can enter questions at any time. And ideally, if you want a specific speaker to answer, please indicate that in the question so that we can direct you to the right person. Finally, last logistic information. If you would like to use closed captioning, it is possible to click on the CC button on the top right of your screen and select your preferred language. So without further ado, we're very excited to host this discussion today. And to kick it off, I will give the floor to our first speaker, Stefan de Wolf, who will introduce himself. So Stefan, thank you so much for joining us, and please take it away.
Yeah, thanks a lot, Elisa. I will try to share that. Okay, so thanks again. I mean, it's really much appreciated to be in this panel. I look forward to the discussion also. So to present myself and also the activities that we do. I prepared a small timeline from basically the time that I have been at KAUST. So basically, we are a group that are focused on making solar cells, devices, mainly with a background on silicon. So what we try to do at KAUST is make silicon-based solar cells. Try to be relevant for the industry, but also try to be relevant for hot and harsh climates. And of course, it's like the silicon industry has evolved a lot in terms of performance and industry lines. We are now close to what actually is theoretical possible. So this is why, and we really try to also formulate strategies to make even better silicon solar cells by combining it with, for instance, perovskite technology. So initially at KAUST, so there was quite significant solar activities already on emerging photovoltaics, OPV quantum dots, and also perovskite. So we started to really work on initially on perovskite single junction cells because the facilities were there, and then but it took a while, but we set up a complete silicon lab also, and our focus is really on so-called silicon heterojunction cells. So this is basically the technology invented already more than 30 years ago by Sanyo, Panasonic. It's basically, I would say, really a prime example of passivating contact technology, which we also see now in perovskites that has become very important. So basically, we have an absorber. In our case, it's silicon. We deposit an electron and a whole selective material, but in between these contact layers and the absorber, you need to passivate as good as possible because this will enable high voltages. We see that in perovskite devices, but actually silicon heterojunction cell also has explored that idea significantly by using amorphous silicon depositions. So once we could make a silicon cell and we could make a perovskite cell, our first focus was, I said we wanted to make a tandem, but of course to make a monolithic tandem is quite complex. So we started with 4 terminal tandems. So initially, one of the focus points was that how do you make a semi-transparent perovskite device? So you need to really think about how to sputter a TCO on a perovskite and so on. And then step by step, we could make better devices. So this was maybe a first, I would say, milestone for tandems, because it's basically we have a tandem 4 terminal that the tandem efficiency is higher than each of the subcells, which is, I guess for most people, the first goal that they want to achieve if you work on tandems. Then, of course, we also realized that probably, even a more impactful approach would be completely to make a monolithic tandem. So with this, we worked together with a group of Ted Sargent. Back then, the group was in Toronto, but we really tried to combine a typical, I would say, industrial silicon wafer with a perovskite process. So, it's a little bit small, but here, a typical industrial wafer will have texture because silicon is a quite weak absorber. So you really need, texture to couple in as good as possible light and also have good internal light trapping. And we combined these 2 technologies by using spin coating for the perovskite. Then again, we want to be as close as possible to the market. So field testing for us from the beginning has already been quite important. So we developed encapsulation routines in our lab and also started to do first outer tests. One interesting approach, and also what you see specifically for large-scale deployment for PV, is bifaciality for silicon. And we also explored this idea for tandems. And actually, it is definitely a valid idea. And the interesting thing of a perovskite silicon tandem is that actually you can use a quite narrow bandgap perovskite, which means you don't have to add a bromide. So you could actually end up with a quite stable composition and have a good device. Talking about stability, of course, very important. The performance has been proven on single junction and tandem level, but now, most of it is question of stability. So we worked a lot on single junction devices because, making a tandem is quite complex. And at single junction level, we worked a lot on 2-dimensional passivation layers. Also on tandem level, of course, passivation is really important because this has been driving our performance. And then, step by step, we improved, how to make a tandem. And then, 2 years ago, we were really happy to have this world record. And I would say there were 2 main developments to obtain that record. One was published actually in this paper, was basically the optical design. So now we have tandems that, from shock liquefier perspective, we have a current that is close to what actually is possible. So there's not too much to be gained anymore for the current. And then second development was actually, we knew that our perovskite, the luminescence, the quantum yield of the top cell was actually quite low compared to a single junction device. And this we also try to improve. And then, now more recently still, we have double-sided passivation strategies with 2D heterojunctions. And then we also work on scalable methods. And this is, the last thing that I would like to show here. We work, not only on spin coating, we also work on blade and slot die coating to make tandems. There was a paper earlier this year published in Joule with a certified efficiency of 32%. And we work also on vacuum-based techniques. So with this, I will close here, and I mean, this is my introduction. Thank you.
Thank you so much, Stefan, for your introduction. And now we're going to move on to Joy.
Great, thank you. My name is Joey Luther, and I'm a Senior Research Fellow at the National Renewable Energy Lab. So NREL started as the Solar Energy Research Lab in the late 1970s, and many of you may be familiar with this plot, which NREL keeps up to date, and it is a sort of a validation and a certified efficiency chart that has basically all solar technologies on there. You can see in the late 70s there, it started with 3,5 materials, silicon, CIGS, cadmium telluride, and amorphous silicon. And as those technologies improved over time, other technologies have been added to the chart. And so NREL got started in the perovskite field in roughly 2013 with Kai Zhu and Joe Barry and myself. And we've been working on this technology for a variety of different applications, but also for the normal application, which is terrestrial solar power generation. And so you can see sort of the highest efficiencies that have been here. This chart is sort of has gotten really complicated, and what that means is there's a lot of research in photovoltaics, and it's very good to see these huge efficiency improvements. And one thing that I really like to point out is that some of these newer emerging technologies, the ones that have sort of the late start date, have now crossed some of the mainstream technologies, and perovskite silicon tandems are a great example of that at over 34%. But in addition to just the simple efficiency value, which is really the maximum efficiency, and it can be a small area and things like that, NREL also has this center that is led out of Sandia, and NREL is a sort of the co-lead of this center. So Josh Stein at Sandia and Laura Schellas at NREL have been working on outdoor testing in the center that's called the Perovskite PV Accelerator for Commercial Technologies, where they accept small modules and tandems and things of that nature, and they field them in a variety of locations and sort of track their performance over time, which is a very valuable asset to emerging technologies like perovskites. And you can go right on their website. The link is sort of at the top of the right side of this graph here. And you can look at both perovskite single junction cells and perovskite-based tandem solar cells, and they categorize them in a variety of ways on this plot based on sort of the area of the module, where they're located, and whether or not the efficiency measurement has stopped. And so you can see if there's an arrow pointing up, that means it's still collecting data. And the y-axis tells you how long it's sort of been in the field, as long as it's above 80% of its maximum efficiency. So if you look on the tandem chart, you can see that there are modules out there that have been for over a year, and they're still over their T80 value in the mid-20s% of efficiency. So this is very valuable data that I think we'll get into a lot during the moderated session on how important it is to understand how these materials evolve over time. And then I just wanted to sort of take a little sidetrack and talk a little bit about some other areas of applications of perovskites that my group specifically is interested in. And one of them is a much smaller market, the space PV market. But if you look at this chart on the left, it shows sort of the total number of satellites that have been in space, that have been launched as a function of time. And so you could see a nice steady increase until about 10 years ago, when the commercialization of launches really took off, and the number of satellites is growing rapidly. And so you can track all the objects in space, as well as all the active satellites, and as well as all the former satellites. And this number looks really impressive, but in the next couple years, big companies that we know like Starlink and Amazon and OneWeb and others plan to launch 100,000 satellites each, just to compete for the internet and cell phone communications market. And so the opportunities that perovskites offer here are also really interesting. And so to sort of work through some of the initial challenges of this, we've launched some perovskite solar cells in a variety of different satellites. You can see on the right there, that's off the International Space Station, and you can see if you the moon is in the background if you look underneath that sort of wing on the right, but you can see a CubeSat being ejected from the International Space Station, which has had perovskite solar cells from our lab on it, and it tracked its 100-day mission, and the solar cells survived. So we're very excited about that. But we also have a variety of other satellites and balloons where we've tested the application. And so this sort of completes, the outdoor testing type of situation where we can start to get them in real world conditions. But obviously we still have a lot of work to do in terms of scaling up the size of the device and achieving full durability requirements for these applications. So I'll stop there, and thank you so much for letting me be a part of this.
Thank you so much, Joey, for bringing this additional dimension to our discussion today. And last but not least, we're going to Anna Maria.
Hello, everyone. I spoiled already the last slide. Voila. Okay, here we are. So thank you, Elisa. And I'm Anna Maria Petrozza, and I'm leading the group of advanced materials for optoelectronics. We are based in Milan. So it's the Italian Institute of Technology Center based in Milan. So I come from the field of organic electronics and dye-sensitized solar cells. And we started working on perovskite in 2012 when I got an email from Henry's Nate asking to look at these magnificent new materials to understand what was the nature of photocarriers in this system. But let's say by the time we put our head around these materials and moving from especially a molecular system semiconductor to a crystalline inorganic semiconductor, we realized that actually not only the nature of photocarrier, but defect would play a fundamental role in the performances of this system. And that's why, since 2016, this is the title of my talk. So if you meet me around, you probably have seen this title here over and over. But then don't just because, it's always the same talk. This is because, the defect chemistry of this system is extremely rich. And one of the most important, selling point of this technology is really the possibility of tuning the bandgap semiconductor by designing the chemistry of the crystalline unit. And this gives the opportunity. That's why we can talk today about, for example, silicon-perovskite tandem junction. When we started working about defect, so the first reason was because of this, defect tolerance the communities was talking about. So we try to understand why what was the role of defect in their defect tolerance in terms mainly on figure of merit or quality of the semiconductor. Then over time, we found out that actually, when we talk about defect tolerance, this doesn't mean it's not related only to the performances, but also to the stability of the semiconductor, of the thin film, and of the device. And this has been the main focus of the last probably 8 years of the research in the group. So we started initially trying to understand what is the model system in the field, so the lead triiodide perovskite, and then we moved to wide bandgap perovskite, still lead based and with a mixed allied composition. And recently we move also to a narrow bandgap system where you start mixing the A-site metal cation. So I hope I gave it a bit of an overview about what we are doing, and I mean, we can start probably discussing about that. Thank you.
Yeah, thank you so much, Anna Maria. Great. Stefan and Joy, if you want to put your camera back on, I guess we can start our discussion. And you've all gave us already a lot of food for thought in terms of this technology being so promising with efficiencies up to 34% at this point, but also a lot of challenges down to the material design approach. So maybe if we just to set the scene a little bit. And maybe I'll ask each of you if you can briefly summarize from your point of view of your own expertise, like what do you think are the key stability challenges to address, and in particular, like what is the most pressing in your view? So I'll maybe start with you, Stefan, and then moving on to Joy and Anna Maria.
Yeah. I would say maybe the three things. I mean, first one is about reverse bias stability. So basically, I mean, very briefly, if you have a module, usually that's a series connection of many cells. If you have a shadowing event of one cell, all of the others still generate voltage, and they can throw that one cell in a quite strong reverse bias. And so for single junction perovskite, I mean, there have been quite a number of studies, really good studies. And the breakdown seems to be quite low, at only like -5-fold in the best cases. And so this is, I mean, probably an issue. We ourselves, together with Barry Rand in Princeton, we did a study on perovskite silicon tandems, also reverse bias. And there, one of the things that we saw is that actually, under the right conditions, if it is monolithic, the monolithic tandem can actually, protect the top cell. And the reason is that, I mean, basically, even under reverse bias, if you have a monolithic tandem, it's always current matched. And the silicon itself, I mean, is actually a very good diode with a very low saturation current density. So basically, if you have a voltage drop over the tandem, because of the fact that that current is so small in the silicon, I mean, most of the voltage will be dropped over the silicon and not over the perovskite. Now, I don't know how much detail I should go, but there have been follow-up studies, and there was actually, I mean, in your journal, Newton, a very nice perspective by Martin Green and colleagues from China. And so basically what turns out to be the case is that also current matching, I mean, like, which cell is going to be limiting will also play a role. And actually, because, I mean, why is this important? Well, having a complete shadowing event over one cell may happen, but it's also possible that you only shade half of the cell. And if you would then have a situation that actually you have more current generated relative in the bottom cell, in the silicon cell, compared to the perovskite, the reverse bias stability will be different than the opposite case. So basically, I mean, very briefly, I mean, later on maybe we can go in further detail, but the optical design of the tandem will also play a role. You need to be, ideally you want to be current matched from pure power perspective, but to protect in all cases reverse bias of a monolithic tandem, you may want to be current mismatched, actually, which comes at an overall maybe small performance penalty, but you will protect your tandem. So reverse bias stability, I think, is one really important thing that will set already, limitations, I think, to technology. And then other parts, I would say, which are common with the thin film, perovskite is definitely light plus temperature under maximum power or under VOC conditions. And then also still maybe a bit more on the mechanical side, delamination because of mismatch of thermal expansion coefficients. So 3 different possible issues.
Yeah, thank you so much, Stefan. I think you've highlighted already quite a few different areas that we can dig into later. And just to clarify, for those that are not super familiar, so what you're saying is basically for the issue of the reverse bias stability in particular, the solution could be at the level of the device design, the architecture of the device, as opposed to like material, material optimization. It's more of a device issue. Okay.
Because you will need to design your module in a way that for 25 years you never end up in a situation that that perovskite cell would break down.
Yeah. Cool. And Joey, perhaps you have something to add in terms of what from your perspective, what are some of the key challenges in stability?
Yeah, I would say, digging into what you just sort of mentioned there is that, okay, so those are the pressing issues, but the physics of what's going on is electro and photochemistry at the perovskite in the interfaces, which is really critical. So trying to understand how the perovskite is interacting with the material which is right next to it is a major concern. And so the bias presents a condition on the perovskite as well as the temperature, if there's thermal component and light. So you sort of have those three types of stressors. And so trying to understand and develop the right interfaces between the perovskite and the contact layers. I think one approach to doing that is to trying to think of how we can make both inert contact layers and completely impermeable contact layers. You don't want iodine from the perovskite to be able to enter into the contact layers. So you want to make basically iodine barriers, or actually all types of ion barriers at the perovskite level. And then ultimately you want to design the perovskite to not phase segregate, especially if you're trying to make a wide band gap perovskite for a perovskite silicon tandem.
Cool. So going back a little bit to material design as well, in terms of what solutions are there. And Anna Maria, what do you have to add to this?
Well, I can move more to the material side. If you look at the material, you start from the crystalline, from the crystalline unit, you talk about point defect, who are mainly responsible for many degradation phenomena. Though, what I found trying to understand the defect photochemistry is that many times we don't know exactly the actual composition of the thin film that we have. So there is still, I think, a very little control of the heterogeneity of this system. So these are very complex composites. And we talk about perovskite, but most of the time you still have unreacted precursor that we are not able sometimes to monitor with most of the current technique that we use. Also the degradation mechanism can be boosted by these, by this complex structure. And so having a full control of it, also depending on the deposition method we use. Stefan was mentioning before, use different type of printing. There are, also vacuum methods. So thermal evaporation also is another process that people use. And still there is very little control about what is really there. If I can comment also about, light, came across, Stefan was mentioning light and temperature, phase segregation. We have, for example, identify, that in a lead-based perovskite, the allied photochemistry is the key in the light stabilization of this. Now, if I want to think of, a bit more, is something more maybe on a low TRL, is that, we know that allied are critical because allied can actually trap carrier. So a way for neutralize these allied, the light photochemistry is to make them electrically inactive. And the introduction of tin, for example, can do that. So wide band gap perovskite based on tin, they are light stable. But then, I mean, you have other issue within, which is no sensitivity to oxygen. So also in engineering, the material engineering can help also engineering the defect chemistry. So we will always have defect in the system. We need to learn how to live with them.
Fair enough. Absolutely. And yeah, sorry, I'm just taking notes. So yeah, I think you guys have mentioned several challenges and several potential solutions, and it seems like we are really in a situation where it's even difficult to really understand the problem at the microscopic level, just because the materials themselves are not well characterized. We don't even know what we're looking at sometimes. So that seems to me a basic challenge as well. But if we think in terms of still, despite these challenges, these cells have certain characteristics, and the materials have certain characteristics that have enabled them to achieve these record efficiencies of 34% that we've just listened from Joy. So if we think about that, so these characteristics that have led us to these massive improvements in efficiencies, how much of those are also the same characteristics that are impeding stability, or is there a hope that at some point we can have a material that's well characterized, efficient, and stable? Like, if that makes sense. So I don't know if anyone wants to go first. I see, Joy, you're nodding. Do you want to take this one first?
No, I think we can go in reverse order this time too, because I think a lot of the times we will say some of the same answers. So maybe if we go in reverse order, it'll give Anna Maria a chance to talk about the possibilities there. I'll go second.
I know, this is a question. Yeah. Okay, maybe let me rephrase the question.
Or maybe we can say, talk about the learning slope.
Okay, yeah. Please do.
No, I mean, for what we have been seeing 10 years ago, everyone was saying, you look at this material and they just vaporize. I mean, they will melt. But as we have seen recently, from the results from many groups testing the devices outdoor, the results are encouraging. I'm not saying that, I didn't want to scare anyone saying we don't know what we have in the film. Probably I phrase it in a bit more too catastrophic way. We know, but we should know better. We should have a better control, especially in terms of reproducibility, lab to lab, but the community is working in this direction, definitely. There are lots of common engagement in this type of activities. So, the answer is maybe
keep trying.
Yeah.
Does anybody want to add anything?
Specifically for tandems, I would say, coming back already a little bit to what I was saying about the reverse bias stability, you want to be probably a little bit mismatched, which is going to come at a certain performance penalty. Even though if you're a little bit curve mismatched, usually it's at least in part compensated by an increase in fill factor. But still, you will lose a little bit in performance. And there, yeah, it would be quite interesting. It was actually, I think, also covered in that Newton paper. How much? Because ultimately, what you care about is not the efficiency. It's basically the energy yield over a whole year or even over the lifespan of your system. And so if you're mismatched, you have to be sure that at any possible conditions, so late in the afternoon, summer, and so on, you always have to be sure that you are, perovskite limited. Mm-hmm. So this will put already a constraint on your energy yield, but it's not completely well known how much that will be. Just to say, yeah, performance stability, I think there is a certain trade-off. And then, of course, also there are more, from a material science point of view, also, if you go to a narrower band gap, sure, you have less bromide also, which can help. So maybe intentionally you want to go to in the research labs, everyone is chasing performance records. But actually, a different way how to look at things is maybe we should start with a simpler composition that we know that will not suffer from certain stability issues. And once you have, a decent stability, only then you start to engineer it towards a better device. It's basically two different angles of attack. And there, I would think that's probably also the approach that, a lot of companies are taking. That, you have, really good results, and the stable devices probably is sometimes a little bit of a performance penalty. But I would say, I have to say we're also guilty of that, but it would be very interesting that if people publish stability data, that they don't normalize their data. Mm-hmm. That they simply show, the actual initial efficiency, and that we get a better grip of how do you combine efficiency with stability?
Yeah, so on that note, are there protocols already that one could suggest people use, or do we lack the protocols to be able to normalize and kind of have a comparable information across labs and whatnot?
But I would not normalize. I would show the actual efficiency, not start from one. But you don't know what one was. Maybe that's because often in a paper you have a record device and then some stability data, but you have no idea. Was this really a comparable device, or was this?
There is not protocol yet, but this is a common feeling. This is something that what Stefan mentioned. I think the field is mature enough now that they say, okay, now we need to care about this. These are not just details. And so I expect that very soon also journals will start, stimulated by discussion within the community, will start requiring this type of information.
So this is maybe an action point we can take out of this webinar. How can we support you in these efforts? And Joey, I don't know if you wanted to add something, but I was also curious, in relation to what we were just discussing. What about the space applications? Are these challenges the same in space, or are there different ones?
Yeah, well, before we get there, I would say my answer to this question was we're sort of chasing the ultimate performance in this case. And what was really exciting to me was when a perovskite silicon tandem was higher efficiency than the very best 3.5 two-junction solar cell. So I think at the time the record two-junction solar cell that was 3.5 based was in the 31.9% or so under one sun conditions. And so when perovskite silicon was able to surpass that value, I was really interested in why it did that. And so, I think it comes down to the tunability of the perovskites. And I think in the 3.5 case, the most practical bottom cell was gallium arsenide, which has a slightly higher band gap. So perovskite silicon tandems were able to sort of better match the band gap pair. And both of the components were, really nicely optimized, where silicon is enjoyed a very long optimization path to get to, a very appreciable efficiency. And then the perovskites, because of their unique defect chemistry and their ability to tolerate the defects, show a really high ratio of the maximum voltage that they can possibly achieve compared to what they actually achieve. So that ratio is really important. So, really, I think your question is about the feasibility of trying to understand what we can build and what might be the most manufacturable or the most scalable and cost effective in the end. And so, I think, at the research stage, we should work on trying to understand what it takes to get the high performance value. And it's totally okay to, work on flat silicon, which maybe isn't the most ideal case, but just to try to understand how the perovskite and silicon pair with each other, and then know that in the future, we're going to go to a textured silicon, and that texture might bring about new stability issues, or we don't necessarily, we maybe take shortcuts in how we manufacture just to get the perfect device, so that we can really study those to figure out if it's worth to put the effort into figuring out how to make it more stable ultimately. So, I think at this stage, we learn by doing. So the more that we can do, the more research that can be undertaken at this stage, the more we'll learn what makes the most sense, feasibility, from a feasibility perspective, to do commercially. Also, I think even the costs of 3.5s can come way down if it achieves a lot of attention. And so the more attention you can bring to a technology, I think the more feasibility that it could have. So in this case, I think what perovskites have benefited from was just an enormous amount of publications, enormous amount of work. Pretty much, every region of the world is working on these technologies, and that's really, really good for the field. And then your second part of your question specifically to me was, do I think space is any different? Yes, space has very different applications. I think the thermal constraints in space are very different, especially if it's in a satellite orbit where it's going behind the Earth. It's really hot when it's in the sun, and then it goes behind in the shade, and it's very cold. And so that thermal cycling presents totally unique challenges compared to what a solar cell would have on Earth. But it has no oxygen or water, and so if you're looking at those types of issues, those are removed. So I think we don't even fully understand all of the constraints that space solar cells go through. It really depends on exactly where their environment is. If it's low Earth orbit or deep space, they're all going to be slightly different cases. So the less we've done in those environments, I think the less we know. But terrestrial Earth application, we know very well, and we know it varies tremendously depending on where it's deployed. And our outdoor test facilities at NREL might be very, very different than the ones I've seen at KAUST, for instance, in the desert environment. So there's certainly a lot of work to do, and I think the feasibility is where we're at this stage.
Mhm. And yeah, I think you've made an interesting point also on to saying, the more something is researched, and perovskite are very heavily researched, the more you learn, the more you, capitalize on that. But then my follow-up question would be, following up on what you guys were saying, in terms of the cost advantage, beside the high performance, my understanding is that one of the reasons why we were first excited by perovskite materials was that you could produce them at much lower cost than silicon, because just solution processed, right? So if we look at the commercial feasibility in relation to the performance and the stability issues, do you have any idea of whether by the time we've solved all of the stability issues, then the cost advantage that perovskite cells might have, in this case, the tandem variety, if that advantage gets eroded, and then we just stick with silicon like we have been for the past 50 years? Do you have any feeling for that?
Well,
I disagree with the cost. Silicon is
Yeah.
very cheap. Silicon, I think one thing that communities sometimes, from my perspective, misunderstands is that you will not beat silicon is something that silicon is doing very well already. So it's like, I'm skeptical about single junction perovskite. If it is meant to replace silicon, I don't think it's going to happen.
I think you have to look at it as new possibilities. Higher efficiency product that can give you a higher energy yield, those types of things.
Yeah, I think exactly. I think there are two ways where perovskite is really meaningful. That is, we are simply at the limit of what silicon can do by itself. So we can use it to boost the performance. And then the other application, I think, is, as I said, applications where silicon is doing actually maybe not the best job, like maybe ultra lightweight applications or seamless integration. I mean, where form factors are important. There are such applications, and often such applications don't necessarily need 25 years of warranty, which is also important. So currently, I think that's basically the biggest issue. It's like, yeah, I saw already, like somebody has that question. It's like, yeah, if you don't get 25 years of warranty, is it over for perovskite? I don't think so, but you will not, yeah. I mean, you need to look for, the right market. And again, we need to go to a society that will be completely electrified with renewable sources of energy. So we just, we install now 2 terawatt globally, or just a little bit more. I mean, there's still a lot of PV that we have to install. So I would not be worried about that perovskite is going to be pushed away by silicon. I mean, it's basically complementary technology. It's not competing with each other.
I mean, if you look at the record efficiency of 34.7 and you compare that to, a full silicon module that's fully optimized, you're getting 50% more power out of the multi-junction case. And so, that just opens up a whole new range of possibilities where you can benefit from, the installation cost goes down and that sort of thing. So, if you were to just look at the cost of silicon, you're going to need that cost still in a perovskite silicon tandem. But, in conjunction, you get a synergistic product where you get certainly higher efficiency, easier installation cost. You can get more power per unit area on a small roof, things of that nature, where there's markets that are just different than, and I think, what we're seeing now as PV is really branching out in its application. So there's a lot more applications. Those different applications want new products, and that's really what this offers.
Yeah. Thank you both. Anna Maria, do you want to add something? No? We can't hear you, but I take it as a...
Yeah, no, I was just saying that, I fully agree with that. I cannot think about perovskite as a competitor, but just...
complementary technology.
Yeah, exactly, and an opportunity.
And we're coming towards the end of the webinar, so there are a couple of questions that I would like to start addressing from the Q&A. If attendees have any other questions, please keep adding them. We will start answering them. There was one that actually disappeared from the list, but it was a question about flexibility. It was whether silicon-perovskite tandem cells can ever be flexible. So I don't know if you guys have an answer for this.
Well, I can answer that. I don't believe in flexibility as an application. I believe in, I would say lightweight applications where maybe, but if you look at silicon alone already, you can easily cover a wing. What do people mean by flexibility? That you have like 10,000 bending cycles? What is the application for that? I don't think there is any application. I think it's a novelty product, but lightweight and integrating it. I actually have a perovskite module from a conference in China, higher in town. It's very heavy. It's glass. So this is something that I think perovskite community definitely in a meaningful way can work on new encapsulation strategies, but especially for space where weight is so important. Also for any airborne application, drones and so on, where you anyhow want to cut down, the weight as much as possible, and you want to be as autonomous as long as possible. But so flexibility, it's maybe my personal feeling, but I don't think that's a real application.
And I don't know if the question meant actual dynamic flexibility or more like curved space, because I'm assuming you could potentially make a curved cell to adapt to an airplane wing or something. That's probably
silicon
possible.
is doing
Yeah, but silicon can do that.
Silicon can do
so it's possible to do
silicon will also be able to do that.
With the tandem as well. Yeah. Cool. And then there's another couple of questions. I think one kind of addressed already, which was, what if the perovskite doesn't become stable as a silicon, as a cell, I'm guessing. yeah, I guess the question is more like if the perovskite bit of a tandem is still struggling for stability, you know, what happens to the whole tandem cell as a whole? And I guess you guys have partially answered this, but if somebody wants to give like a wrap up answer.
Yeah, I think there's a lot of room for outside the box thinking on this. You know, if you have these are sort of just weak ideas. I think we can ultimately improve the stability of the perovskites to be good enough. But if you could enable a 3-terminal tandem where you have a contact in the middle, and you had a bifacial silicon, if you really wanted to, you could flip the solar cell around, you know, and let the backside be the incident side after the perovskite. If it were to degrade, that could be sort of a backup plan. But I think there's ways to sort of recycle or design it in a way in which you could regain that efficiency after some period of performance. I think there's a lot of opportunity for sort of outside the box thinking and rethinking the way we handle a module.
And actually, on that note of recyclability, there's another question that is asking about we haven't spoken about toxicity at all for some of the perovskite materials in particular. Like, do you have any views besides the issues of stability? You know, what are the challenges related to recycling these materials, in relation to their toxicity?
Yeah, I mean, first of all, I would say that, this question is giving toxicity for granted, but there are lots of studies who are still trying to understand what is the level of toxicity. I mean, having lead doesn't mean necessarily that there is lots of work that need to be done to understand what happened to perovskite when a cell, get broken. In a specific soil. So there are lots of scientists working in the field of environmental science who are trying to understand it. And so I would not, take it it's not something already clear already. So this is one point. And this probably is the first answer to this question. Then perovskite, I think they have, they are easy to break. This is a problem, maybe, was the starting, why people were initially skeptical about this material, but this can be, also taken as a strong point for the recycling of this system. And there are also more and more investigation in this direction. I mean, as an ionic solid, is much probably easier to be recycled than many other materials.
Yeah, that's fair enough. And I think, again, based on one of the questions that's there, but also what you guys were saying earlier, you spoke also about interfaces, the importance of the interfaces besides, the actual perovskite material. But could we dig into that a little bit more? So what basically, if we think about the interfaces between the perovskite, the silicon, the perovskite, and maybe the capping layer or whatever other layers in the structure, what do you think that are the main challenges? And the question was asking specifically whether ITO and or IZO can be considered as inert interconnection layers for tandem. So I don't know if you want to answer this specific question or more broadly the point about interfaces and what can we say in more detail about that particular issue?
I mean, if I can start, more generally, from a more general point of view, I think where the community is going is really trying to understand which are, designing actually the right interface of perovskite with other materials. Because everything started with a model system, perovskite, lead, triiodide. But of course, we are moving to wider band gap, and we are still using, for a long time, we are using the same charge extraction layers. So that is definitely a critical point for many reasons. I mean, first of all, starting from the crystallization, when I was telling you that sometimes we don't know what we have, is also because if we use a different type of charge extraction layer, a different type of substrate, the material is crystallized in a completely different way. And yeah, so in this direction, also in terms of stability and what is going on, is definitely still a critical point to be addressed. There is no rule at the moment.
I mean, from my side, I would say, I mean, there's of course many things you want to have right at an interface. I mean, you need energy alignment, you need to passivate defects and so on. But most of these things, I think, are a question of engineering. I mean, we can find contact materials with the right work function for a given band gap and so on. I mean, this is all solvable. The thing that I'm most, I would say, concerned about is actually what Joey was saying, is iodine moving around and interacting. I mean, it's for sure that it's constantly moving around in your material in a bulk. I think it's virtually impossible to stop that. And then, yeah, how to avoid that is going to interact with your interfaces over 25 years of day and night cycles. I mean, yeah, we work on these two-dimensional perovskite layers where in the bulk of the 2D, you have this, I mean, the ion migration is much less. But still, yeah, I mean, for me, that's probably the most fundamental challenge.
Joe, you want to add anything? If not, I think...
No, I think...
Yeah, sorry, that might be, I think there's a little bit of delay on my part. I was just saying, maybe we only have a few minutes left. I will just take one final question from the audience, which maybe it's for you, Joey, because it's to do with kind of standards and protocols to evaluate the reliability. And the person is saying how standard protocols used for evaluating technologies can be directly applied to assess the reliability of perovskites. For example, ISO protocols provide some guidance, but they may not apply for from the perspective of space standards. So the question is, what would be the best practice to evaluate perovskite cells, given the lack of consensus on how to properly assess them? So I guess this goes a little bit to the work that NRL is doing in terms of certification, but beyond that as well, you know, do you guys have any idea on what, you know, what would be a good protocol to assess perovskite, going also a little bit back to what we were saying earlier?
Can you hear me okay? My sound is...
It's a little bit funny.
Yeah. So, you know, I think the clearest way that we can evaluate the stability is by increased temperature performance. I think, you know, testing the devices at 85 C for long periods of time is good. But in reality, we need 5-year outdoor data, we need 10-year outdoor data, we need 15-year outdoor data. And then we'll understand, you know, at the shorter end of the testing cycle, we can understand more about how these relate to 5, 10, and 15 year. Right now, you know, we're basing it on 1,000-hour stability, we're basing it on 1 year outside, and we're trying to figure out what mimics that case in a fast testing example. But ultimately, we're just going to need a little bit of time, and then we're going to need to understand how these sort of accelerated tests play out.
Thank you. Anna Maria, Stefan, do you want to add anything?
My feeling is that, I mean, again, to come back to that iodine interaction, I have the feeling there's not really a test that is probing that well. I mean, like for instance, I mean, in Potsdam, I mean, they really did very nice work on fast and slow hysteresis, and then they really see that, I mean, the amount of hysteresis correlates with stability of the device. And hysteresis, has of course a lot to do with ions moving around. And I think it's from a pure, maybe simplistic, mechanistic view, if things are constantly moving around in a material, I have a hard time to believe that's 100% metastable. So I think we need to have a test that's very fast, well, at least cycling constantly the ions. Many cycles, maybe even just in the dark, maybe at the given temperatures, and that this should become kind of a standardized protocol, or at least to see if it would make sense to make it a protocol. A quite simple test that constantly sweeps basically IV curves, and not just keep it at maximum power point, which is the usual thing around the VOC. Not a steady state, but really kind of a dynamic test.
If I can just add something, just a further complication rather than clarification. I mean, at the moment, different type of charge extraction layer are tested, and the chemistry, so the interaction of this ion with these materials, I mean, is a zoo of processes all the time. I mean, just to say, I mean, if you have iodine and you have an organic molecule, they are strong, strong electron accepting materials. So you can imagine that, I mean, many things can happen and really depend also on the organic or the oxide materials you have. Mm-hmm. So, yeah, the direction is that one.
Cool. Thank you for all of your insights. And I think with this, we come to the end of our session because we are at the end of the hour. I would like to take the chance to say a heartfelt thanks to the three of you, Stefan, Joy, and Anna Maria, for giving us your time and discussing this interesting topic with us. I think I learned a lot. I have even some things that I can follow up on the editorial side of things. So thank you so much. And I would also like to thank the audience for tuning in today and being very active in the discussion. Again, we hope this webinar was useful for you as well. If you missed anything during the webinar or want to listen to it again, you can watch the recording that will be available shortly on cell.com. And you will also receive a survey by email that we would be very grateful if you could reply to, so that you can give us some feedback, and so that we can keep improving this series of webinar in the future. So with that, I would like to thank you everyone again for your time and the very useful discussion, and we hope to see you again at another CellPress event. Thank you, everyone.
Thank you.
Thank you. Bye-bye.